Okay, now we'll continue with Worksheet 7E with problems 3 and 4. Problem 3 is like the other webcast that went through the slides on the energy of satellites. This was a problem very similar to the last example in that set of slides. But here we've got a planet orbiting a star, and so the star is like a sun, right? So that is the central mass. They're telling us the period and the semi-major axis. So the semi-major axis, that's our clue that this is an elliptical orbit. So we've got a semi-major axis of 6.89 e to the 10th meters, a period of 8.38 e to the 6th seconds, and we're looking for the mass of the star. So that is the central mass, or the larger mass. So since the information we have to deal with here is period and semi-major axis, it puts me in mind of Kepler's third law, which says that the square of the period is proportional to the cube of the semi-major axis. And so I'm going to want to solve for the large mass. And so let me move the equation around here before I start plugging in. So I'm going to have that the mass is going to be 4 pi squared over g times t squared times a cubed. And I'm just going to plug the information that I have in here. Uh-oh, I plugged A in for period. That's not going to work. See, I need this to be period squared. And then A, the semi-major axis, has to be cubed. Okay, so we'll plug this in to the calculator. Okay, so I get a mass of the star that's 2.757 times 10 to the 30th kilograms. Okay, then it wants to know the total energy of the planet in this orbit, or I'm sorry, it's giving me the total energy, is this negative 1.34 times 10 to the 37 joules. We want to know the mass of the planet, and that is the smaller mass. And so I'm going to use the equation for the total energy of a satellite in an elliptical orbit. That's negative g times the product of the masses divided by 2 times the semi-major axis. It's semi-major axis because this is an elliptical orbit, and I'm going to want to solve for the smaller mass. Okay, and so that smaller mass would be negative the total times 2 times A divided by G times the big mass. big mass is what we got from part A of this problem. Okay, you see that my negative signs cancel out here. So and so I get a small mass of 1.004 times 10 to the 28th kilograms. Okay, and let's go ahead and look at number 4. This is a real-life situation. The Chandra X-ray Observatory is in an elliptical orbit around the Earth, and it goes out into the Van Allen radiation belts. Okay, so anyway, the orbit takes it to a maximum altitude of 133,000 kilometers and a minimum altitude of 16,000 kilometers. So what that's telling me is that the R-min is the radius of the Earth plus that 16,000 e to the third meters, right? R max, and actually maybe I'm going to actually calculate that. R max is going to be the radius of the Earth plus this 133,000 times 10 to the third meters. Okay, so I'm just going to calculate R min and R max. The radius of the Earth is 6,380 kilometers. Don't forget to convert that also to meters. So the minimum R for the Chandra is 7,980,000 meters, and the maximum is 139,380,000 meters. Okay, so we have our min and our max. It's asking us the semi-major axis. So that's A. And I know that A equals 1/2 of R min plus R max, right? Because together they add up to be the entire major axis. So the semi-major axis is half of that. So this is going to be half, well, I'm not going to write it down, but we've written them over there. So I'm just going to add those two things up and divide by 2. So our semi-major axis is 7 million. Oh no, it's going to be bigger than that. Sorry, it's going to be 7,368 with 4 zeros. And so that's 73,680,000 meters. The eccentricity is D divided by A, and D is A minus R min. And so the eccentricity of this orbit is going to be the number we just found, minus R min, divided by the semi-major axis again. And so that's 0.892. Okay, and then it asks for the total energy associated with this orbit. The total energy for something that's in an elliptical orbit is negative G times the product of the masses divided by 2 times the semi-major axis. Our big mass here is the Earth. The small mass is Chandra. And remember, the total energy is going to be negative since it's a satellite. Okay, so I've got G times the mass of the Earth and I get negative 1.297 times 10 to the 10th joules.